Hello students. So today we discuss the topic of principle of microscopic reversibility and Onsager reciprocity relation. Onsager is the first scientist whose relations are used to explain the thermodynamics of irreversible processes. So Onsager, first of all, Onsager derived the various relations which describe the qualitative aspects of the irreversible processes. And according to Onsager, the thermodynamics of the various irreversible processes, these are based upon the three main concepts or three main laws. First is the principle of microscopic reversibility. Now, what is the principle of microscopic reversibility? In a mixture which is at equilibrium, the rate of the forward process is always same as for its reverse process. So basically, the principle of microscopic reversibility, it deals with the system which is very close to the equilibrium and it behaves just like the equilibrium state. And as for the equilibrium state, rate of forward direction becomes equals to the rate of the backward direction. The same is the principle of microscopic reversibility. So all the particular processes which proceed at the same rate in both directions, either in forward direction or in backward directions, if their rates are same, then this is known as the principle of microscopic reversibility. Second is the linear law. Linear law, it holds good only when a system which is under study, it is very close to the equilibrium. As we already know, in the irreversible thermodynamics, we always deals with the stationary state or steady state, and this is the state which is not an equilibrium state, but this is a state which is very close to the equilibrium state. So Onsager, it gives the three main laws or three main concepts which are applicable only to the state which is very close to the equilibrium state. So this is the second law, which is known as linear law. Under linear law, there is a relation which is known as linear relation. Ji, which is flux. Flux is equals to Lij into Xj. Xj is the force and Lij जो है, these are known as the phenomenological coefficients. And such kind of relations, they are known as phenomenological relations. And according to such relations, flux is always directly proportional to the forces. So if the force or generalized force or driving force is high, flux is high. If the driving force is low, flux is also low. Third is very important, which is the Onsager reciprocal relation. According to the Onsager reciprocal relation, basically the two cross phenomenological coefficients, they are always equal near the equilibrium state. Lij and Ji, these are known as cross phenomenological coefficients. If both are equals near the equilibrium state, this is the Onsager reciprocal relation. And in theory, for a particular selected pair of fluxes and forces, the matrix of phenomenological coefficients would be symmetric. This is the definition of Onsager reciprocal relation. And in this, under this definition, you can see we have to select a pair of fluxes and forces. We have to select a pair, and only for that pair the cross phenomenological coefficients, they are equal. This equation is known as Onsager reciprocal relation. And what is the physical meaning of this relation? According to this relation, Lij represents the effect of force J on I. This is Lij. This is always equals to Lji, which is the effect of force I on flux J. This is the physical meaning of these cross phenomenological coefficients. So these are the three laws on the basis of which the thermodynamics of various irreversible processes are explained by the Onsager scientist. Now, in the Onsager reciprocal relation, there is a word that selected pair of the forces and fluxes. Selected pair. So, what is the choice of flows to form the conjugate pair? Basically, there is no specific rule. There is no specific rule which pair forms the conjugate pair, which is the specific pair. Let's take an example. Basically, I have one dimensional metallic rod. In this metallic rod, the temperature difference is there is the temperature difference at the both ends T1 and T2, and at the same time there is the potential difference. Due to the temperature difference, the heat flows through the rod, and due to the heat flow, heat flux जो है that is produced, and due to the potential difference, current flows through the system, and due to this current flow, electric current flux is produced. Electric current flux is represented by Je, and heat flux is represented by Jq. So by seeing only this condition, this situation, we can say Je and Jq, current flux and heat flux, they can form a conjugate pair, but they do not form a conjugate pair. This is not a pair for Onsager relation. However, electric current, it forms a pair with the entropy flux, because entropy at one end is different as compared to other end. Entropy is the randomness in the body, and since at two ends there is the temperature difference, so due to the temperature difference, the randomness in the molecules is also different. So at both ends there is entropy difference also. There is also the entropy difference. Due to entropy difference, entropy flux is produced, and electric current, it forms a pair with the entropy flux. Okay. Now why, there is a question comes in everyone's mind, that why electric current do not form a pair with the heat flux, but it forms the pair with the entropy flux. This is because there is no specific rule. There is no reason, no specific rule which describes that which pairs should be formed or which pairs should not be formed. It is totally random selection of the pairs, and what kind of the pairs are formed, it is experimentally studied. That's why we take this example. Okay. Now for this system, one dimensional metallic rod, if J1 is the electric flux which is passing through it, so J1 is equals to the product of the phenomenological coefficient into the force L11 x1, L12 x2, L13 x3. These are known as the conductance coefficients L11, 12. Okay. Now Onsager reciprocity relation. Onsager reciprocity relation. What the relation? Lij is equals to Lji. This is possible only for the systems which with these very small or considerable deviations from the equilibrium. So basically, in simple form, this relation is valid only for the those systems which is close to the equilibrium, but it is not at equilibrium. Okay. So this is basics about the principle of reciprocity relation. So next is that is very important topic. It is Onsager reciprocity relation. So as we already studied, what is the Onsager reciprocity relation? That is Lij, this is equals to Lji. So under this topic we prove that Lij is equals to Lji. So this is the proof of the Onsager reciprocity relation or derivation or proof. Onsager relation is based upon the principle of microscopic reversibility. What is the principle of microscopic reversibility? For any molecular process and the reverse of this process, they will take place at the same rate. That is, rate of forward reaction is equals to rate of backward reaction. That state is known as principle of microscopic reversibility. And according to principle of microscopic reversibility, L11 and L21, they are equal. Both are equals. Lij and Lji. I and j both are different, 1 2 or 2 1. So to prove this relation, we consider a coupled cyclic process, a cyclic coupled process. That is, A is changes into B, B is changes into C, and C is changes into A. So this is a cyclic process. If we start from A, then we reach B, and B to C, C to A. All these three elementary processes, all these three processes or relations, these are known as elementary processes. They all are under equilibrium with one another. A and B is in equilibrium. Rate of forward reaction is K1. Rate of backward reaction is K minus 1. B to C is the rate constant is K2, and if C to B, rate constant is K minus 2. Similarly, for C to A, K3, and A to C, K minus 3 is the rate constant. For these three elementary processes, let us suppose J1, J2 and J3. These are the net rates of these relations. And according to the chemical kinetics, now we find out these rates. J1 rate first for A to B process. J1 rate is equals to K1 rate constant for the forward direction into concentration of A minus concentration of B और rate constant है K minus 1. The first rate constant can be written by seeing A component. B to C ਦੇ ਲਈ we will look for the B component. B to C, K2 into B minus K minus 1 into C, and similarly for C to B, K3 into C minus K minus 3 into Ca. So these are the three net rate constants, and this is my equation number 1. As you can see, in these elementary processes, A to B, B to C, C to A, if A is a product, A is a reactant, B is the first product, C is the second product. For everyone we take coefficients as 1. So we suppose that in this process all the stoichiometric coefficients of all the species are taken as 1. Now the affinities of these reactions. Affinities. What are affinities? Affinities are basically driving force, generalized force or driving force, which we represent earlier as X. Okay. This is the generalized force. Generalized force is also known as affinity, and affinity is represented by A. So for these three processes individually, we will write affinity for first step A1, affinity for second elementary process A2, and for the third elementary process A3. For A1, first elementary process, A changes into B. So chemical potential of A minus B. B to C, A2, chemical potential of B minus chemical potential of C. This is for B to C. Simply subtract their chemical potentials. This is for C to A. This is for A to B. Simply subtract their chemical potentials. So here you can see A3 can be written as, if we add A1 plus A2, this is A1, this is A2. When we add A1 plus A2, chemical potential of B cancelled out. We will get only chemical potential of A minus chemical potential of C. A minus C. Minus is taken common. This will become chemical potential of C minus chemical potential of A. What is mu C minus mu A? This is A3. Okay. So A3 is written as minus, if we take minus as common, A1 plus A2. This is my second equation. Now this relation you have to learn, because the derivation of this syllabus is not in your syllabus. T into dis divided by dt. T is the temperature of the study. Dis, S represents the entropy. Di, I represents the entropy of the internal system. So this is the change in the entropy of the system with time. This is equals to T theta, and T theta is equals to Aj. A affinity, J flux. Aj is always greater than 0. What is T theta? T theta is known as dissipation function, and its units or its dimensions are energy per unit time. T theta is basically a measure of local dissipation of free energy. Local dissipation of free energy. This is the meaning of T theta. So now we pick only these relation. T theta is equals to Aj, and since we study 3 different elementary processes, so T theta for all these 3 reactions, it is written as not Aj, but it is Ai, Ji. I varies from 1 to 3 for all the 3 processes. When we open this becomes A1 J1 plus A2 J2 plus A3 J3, and A3 can be written as minus A1 plus A2. So this you can see from the equation number 2 from here. So now next just rearrange it. Make the coefficients of A1 in one bracket. First J1, and from the second bracket from A1 minus J3 comes. Then for A2, there is A2. For A2, the coefficient is J2, and from second one it comes minus J3. So T theta can be written as J1 minus J3 into A1 plus J2 minus J3 into A2. So this J1 minus J3 and J2 minus J3, these are written as J1 minus J2, A1, A2 affinity, A1, A2 affinity. The phenomenological coefficients are L11, 12, 21, 22. Okay. Next we apply the principle of detailed balance on above equations. Now, what is the principle of detailed balance? This is basically the special case of the principle of microscopic reversibility, and according to the principle of detailed balance, basically the rates at equilibrium state, they are not only equals to each other, but they are also equals to 0. J1, J2, J3, these are the rates of the 3 elementary processes, and when these processes are at equilibrium, we represent here E. E represents equilibrium. The rates are not only equals to one another, but they are also equals to 0. This is the principle of detailed balance. Now we use this principle of detailed balance on the above system. Since now principle of detailed balance, it applies to the systems at equilibrium state. So let us suppose at equilibrium the concentration of ith species, suppose करो A species, B species or C species. At equilibrium state their concentrations are CIE, means CAE, CBE, CCE. These are the concentrations at the equilibrium conditions. Okay. Now we use the equation number 5, that at equilibrium their rates are 0. Now go back to the equation number 1 here. From equation number 1, when there is equilibrium state, just simply represent E at all. And according to the principle of detailed balance, left side is equals to 0. So if I take only first case, so K1 CAE, this becomes equals to K minus 1 CBE, because left side is 0. Similarly, from the second equation, K2 CBE becomes equals to K minus 2 CCE. From third equation, K3 CCE is equals to K minus 3 CAE. So these three equations we will get at the equilibrium state. Now we introduce another term, which is alpha I. Alpha I is what? This is the another parameter which gives us the difference between the concentrations. C represents the concentration of the ith species minus concentration of the same species but in the equilibrium state. Okay. So from this relation we can find the concentration of the ith species. Let me take an example. Suppose when we start a chemical reaction, A component is 100, and after some time when A changes into B, equilibrium is reached. When the equilibrium is reached, A component reduces to 80. Okay. So 100 becomes concentration of A and 80 becomes the concentration of A at equilibrium state. So difference between 100 minus 80, this is 20. 20 is basically the alpha A. This is the difference between the both concentrations. So concentration from this relation, Ci can be calculated. इन्हों दूजे साइड ले जाओ, CIE plus alpha I. So from this relation we find all the three concentrations. Ca, I को replace I with A, replace I with B, replace I with C. This will become my equation number 6. Okay. So now as we know, mu A and mu B, these are the chemical potentials, and mu A, it can be written as mu A naught plus RT log concentration of A, and concentration of A, as we can see from equation number 6, it is CALE plus alpha A. In the next step, CAE is taken as common, and in the bracket we will get 1 plus alpha A divided by CAE. Now use the formula log m into log n, log m plus log n. Open the bracket, multiply RT with both terms. Okay. First two terms, mu A naught plus RT log CAE. This will becomes, since here the concentration is at equilibrium state, so this becomes the chemical potential of A in the equilibrium state, and the second term is written as such. Okay. So similarly, as we derive the expression for chemical potential of A, similarly we can write the chemical potential of B. Just replace A with B. That's all. A with B. A with B. So we will get two values, mu A and mu B. And we know what is A1, affinity. That is A chemical potential minus B. In the starting, we write these expressions. You can see for all the affinities. First expression, A1 is mu A minus mu B. Okay. And at equilibrium, when the equilibrium is reached, we know for A to B process, when the equilibrium is reached, so chemical potential of A, it becomes equals to B. So in these two equations, first and second equation, for A1 you have to subtract 1 minus 2. You have to take 1 minus 2. So first two terms, they will cancel out. You are left with second terms. In the second terms, RT is common. So take RT as common. So this is from first equation minus this is from the second equation. Okay. So now for more simplicity, as we know, the concentration of the reactant initially and at equilibrium state, they are nearly equals to each other. They are nearly equals to each other. This is our assumption, or you can say this is present in irreversible processes. That equilibrium state is not different from, much different from the initial state. So if both are nearly equal, so their difference is what? Alpha A. It is very small. If alpha A is small, so when we divide alpha A with CAE, this is also very small. Okay. So in the seventh equation, in equation number 7, first term log 1 plus alpha A upon Ci. This term, it can be reduced to only alpha A upon Ca, because when x is small, then the mathematical relation is log 1 plus x, it is approximately equals to x when x is small only. Okay. So from similarly for the second term, this is reduced to alpha b upon cbe. So seventh term जो है, it is seventh equation, it is reduced to a1, this is equals to rt, first term minus second term. Okay. Now multiply seventh this equation with k1 और k minus 1. फर्स्ट जो ब्रैकेट वाली टर्म है उसको मल्टीप्लाई करो k1 के साथ, माइनस सेकेंड वाली को मल्टीप्लाई करना है k माइनस 1 के साथ. ओके. तो सेकेंड इक्वेशन में जो लोअर पार्ट है k माइनस 1 इंटू सी बी ई, दिस इज बेसिकली इक्वल्स टू k1 सी ए ई. ये इक्वेशन नंबर 5 से उठाया है. नाउ यू कैन सी इक्वेशन नंबर 5. Equation number 5. When we apply the principle of detailed balance, that is equation number 5, this one, we get these equations. So you can see first equation, left side can be replaced with right side can be replaced with the left side. So now in this equation we simply replace this with this. Now take the LCM. After taking LCM, we will get the equation number 8. Okay. So the next step is to find out the value of this. इसकी वैल्यू कैलकुलेट करनी है. ओके. फर्स्ट इक्वेशन जब हमने स्टार्ट किया था, देन वी राइट द रेट ऑफ द फर्स्ट रिएक्शन J1, that is K1 Ca minus K minus 1 Cb. Okay. Ca is written as CA can be written as CAE plus alpha A. CB can be written as CBE plus alpha B. Okay. So in the next step, simply open the brackets, multiply K1 and K minus 1. Okay. In the next step, replace this with this from equation number 5. Same expression. Okay. As first term and last term, it will cancel out, third term will cancel out, we are left only with the second term and fourth term. So this is J1. Now you can see from equation number 8, the upper term can be replaced with J1. Upper term can be replaced with J1. So eighth equation becomes A1 is RT J1 upon this. From this equation, after rearranging, just find out the value of J1. J1 comes out to be A1, K1 और CAE लेफ्ट साइड पे आ गए, डिवाइड कर दो RT के साथ. So this is the expression for J1. Similarly, as we derived the expression for J1, you have to directly write the expressions for J2 and J3. How you can write these expressions? Simply, when we go from J1 to J2, replace 1 with 2, A with B, that's all. So you can see K1 to K2, A1 to A2, A से B हो गया. And when we go from J2 to J3, replace 2 with 3 and B with C. You can see 2, 3, B, C, 2 to 3. Same expression, just change the numbering. Okay. Third, J3 expression is more rearranged. In the J3 expression, we get A3. In the starting, we know A3 is minus A1 plus A2. So this will become this one. So we have three relations, 1, 2 and this one 3. These J1, J2, J3, these relations are used to derive the expressions for J1 minus J3 first and then J2 minus J3. So for J1 minus J3, simply subtract J1 minus J3. J1 minus J3. This is the expression for J1. This is the expression for J3. माइनस माइनस प्लस हो गया, यहाँ पे प्लस आ गया. फ्रॉम फर्स्ट एंड सेकेंड टर्म A1 कोफिशिएंट A1 के कोफिशिएंट्स सेपरेट कर लो और A2 के कोफिशिएंट्स सेपरेट कर लो. दिस इज़ फ्रॉम दिस वन एंड दिस इज़ फ्रॉम दिस वन. ओके. एंड A2 के जब ब्रैकेट ओपन की थी तो A2 का भी सेम कोफिशिएंट आ गया. A1 के कोफिशिएंट में RT इज टेकन एज LCM, सो अपर वाले सिंपली ऐड हो गए. सो दिस इज माय एक्सप्रेशन फॉर J1 माइनस J3. In the same way, we can write the expression for J2 minus J3. Here you can see only J1 is replaced with J2. So 1 is replaced with 2. That's why A is replaced with B in equation number 9. You can see 3 and C, they are taken as such because we are taking J3. J3 से माइनस करना है. 9th इक्वेशन में भी J3 से माइनस हुआ था, 10th इक्वेशन भी J3 से माइनस करनी है. तो सिंपली डायरेक्ट रिजल्ट लिखना है. K1 is replaced with K2, CA is replaced with CB, K3 and CC, they are taken as such. Okay. A1 is replaced with A2 and A2 जो है it is replaced with A1. 2 को 1 से replace करना है और 3 and C they are taken as such. This is my equation number 10. Okay. Now I have to compare the equation number 9 and 10 with the previous equations. Just see the equation number 9. In the ninth equation, left side is J1 minus J3. On the right side, there is some coefficient of A, some coefficient of B. Okay. Some coefficient of A, some coefficient of B. Ninth equation. Go back to the previous equation number 4. This equation. Left side is J1 minus here comes J1 minus J3. Left side is J1 minus J3. Right side there is some coefficient of A, some coefficient of B. So when we equate this equation number 4 with equation number 9, left side are same. J1 minus J3 is here. Ninth equation में भी J1 minus J3 था. इस इक्वेशन में A1 का कोफिशिएंट दैट बिकम्स इक्वल्स टू द कोफिशिएंट वी गेट इन नाइन्थ इक्वेशन एंड A2 का कोफिशिएंट जो है L12 वो भी नाइन्थ इक्वेशन के इक्वल आएगा. अगर लेफ्ट साइड इक्वल है तो राइट साइड भी इक्वल्स आऊगी. सो ऑन इक्वेटिंग 4 and 5, 4 which equation number 4 L11. This is the coefficient of A1. L12 is the coefficient of A2. This is from equation number 4. From ninth equation, you can see first bracket, this is the coefficient of A. Second bracket is the coefficient of B. Okay. So, on comparing these two equations, we will get the expressions for the two phenomenological coefficients L11 and L12. Okay. Similarly, we compare the equation number 10 J2 minus J3 with equation number 4. Equation number 4. This is the equation. J2 minus J3 left side is same. On the right side we have A1 and A2. Coefficients are L21, 22. L21, 2, 2. So L21, this is coefficient of A1, this is the coefficient of A2. A1 का coefficient है second term वाला, ठीक है, और A2 का coefficient जो है this is of the first term. Okay, now simply see all these four phenomenological coefficients L11, L12, L21, L22. You can see L12, L12 and for L21 the right sides are same, the expressions are same expressions. So L12 this is equals to L21, but there is some value, they are not zero, they are non-zero. L11, L22 they are different. Okay, but L12 and 21 the cross phenomenological coefficients they are equals to each other and they are non-zero. So this is the Onsager reciprocal relation. This is what that we have to prove, the Onsager reciprocal relation.